This is intended to help people who might be attending the forthcoming workshop. But I do have to confess, I'm not an expert on how information might be used in biology. But one has a general confidence that it's one of the powerful ideas which emerged in the 20th century. Maybe the best proof of that is that there is a New York Times bestseller by James Gleick. How many of you have seen a book called The Information? Okay, it's a strange title, The Information. It's a bestseller. I'm glad not too many of you put up your hands, because if you did, some of this lecture might be redundant, but it's a great book. Okay, and the format is 2 sessions separated by a decent break. Today, similar format tomorrow, and I didn't intend it, but the subject will be handled in a kind of reverse chronological order. So we'll start with the notion of information proposed in telecommunication by Claude Shannon, 1948. We'll move on to statistical inference, and I think those two will happen today. Tomorrow, the slightly older but still alive notion of information and statistical mechanics governing physical systems will come in. And the last session is number 1 for spillover, and number 2, I'm kind of aware that not everyone loves mathematics. Okay, and I've been teaching in the Azim Premji University, and I teach an audience of biologists, economists, and some humanities people. So, you know, earlier I moved amongst people where the selection criterion was that they were comfortable with mathematics. So I'll try and gradually ramp up the mathematical level as we go along, and for a few people who might be interested in actual proof as opposed to simple examples and plausibility arguments, maybe we'll keep some of the last session for that. But maybe I'll even produce a problem sheet by then. The other thing is, I have managed to produce a kind of set of lecture notes as of early this morning, but I didn't manage to get them onto any respectable site. So there are some go.jl kind of addresses which I will give you. Write it up.
I'll put them on there.
Oh, okay, great. So it's already available to you. I mean, at some point it will go to some more respectable place like the Azim Premji website or something. Okay. So let's begin with Claude Shannon, who in 1948 was working for the Bell telephone company and not publishing very much actually. Apparently people told him, look, you've been around a couple of years, why don't you publish something? So he published these 2 papers in something called the Bell System Technical Journal. They were called The Mathematical Theory of Communication. Quite a modest title, and but quite an ambitious goal, because he really wanted to abstract what was happening in many different ways: telephone, telegraph, even the written word, all forms of communication in some sense. And his one central brilliant idea was the following, that if I send you a message and we have to assess what's the information content in that message, a good way of doing it is, if you already knew what was in that message, the information content is 0. You already knew it. So clearly, before the message reached you, you were in a state of ignorance. So if you can quantify ignorance, you can quantify the information which you receive when that ignorance is removed. Okay, so what is ignorance? Well, profound question. So again, Shannon chose a practical model of ignorance. Okay, that there are some finite number of alternatives, and in the simplest case they are equally probable. Okay, so the number of options, let's call it W, and that's a reasonable measure of your ignorance. And then W collapses to 1 when you receive the message. So to take a personal example, 30 plus years ago, I was in the corridor of St. Philomena's hospital, and a nurse came holding a bundle, right? And she said, it's a girl. So W was 2, and therefore you could take that 2 as a measure of information. And in fact, Shannon chose this as the unit of information, okay? The bit. He coined the term bit, by the way, in that paper. Bit being an abbreviation for binary digit, So you could encode boy, girl by 0 and 1, and I am not going to say which stands for which. Okay. Now, so far so good, but actually I was not the only one standing in Philomena's hospital. So let's imagine there were 3 of us. Okay. Then how do we do that? Assuming these are all independent events, what is W when there are 3 anxious fathers waiting? So that, or in general, if you want to generalize, if you have W1 and W2, so 2 different situations which are independent, then the total number of options, and we are keeping it simple, everything is equiprobable. So obviously that's W1 into W2. No harm in using this product as a measure of information, slightly inconvenient. We had a reasonable unit of information or of ignorance. My ignorance and your ignorance combined, you would like them to add rather than to multiply. And the simple solution to that is to take the logarithm. Okay? So Shannon defined an h, which was the log of W. Okay? Now, when you take logs, there's always the freedom to choose the base, but he chose the base to be 2, and that's a convenient choice because this simply means that if W equals 2, h is equal to 1 bit, and if say W is equal to 8, 3 expectant fathers, then h is equal to 3 bits, right? And it's true that if you wanted to represent the possible results of this experiment, either with 3 coin tosses or 3 births, they could be represented by 0, 1, 1, 1, 1, 0, etc. 8 of them. Okay? So that's the simplest possible measure of information, the logarithm of the number of options where all the options are equally probable. Okay? And it has a nice property of being additive in 2 independent situations. Now clearly this needs generalization, and Shannon provided the generalization. So first, let's look at the generalization when you have a larger number of options and they are not equally probable. Okay? So you have I going from some 1 to some S, and each one of these has some probability. Okay? So I don't know if you like pictures, I could represent the probabilities by some things. They're not uniform. Right? So this is P1, this is P2, and of course if you add them all up, you'd better get 1. So this represents a situation of ignorance. You have S possible outcomes. So to make contact with messages, think of these as letters of an alphabet. Okay? So the message consists of letters of an alphabet, and now we are focusing attention on one letter. But we know very well the letters are not equally probable. E is more probable than X or Z or something like that. Okay? So how can you express the amount of ignorance in this kind of situation? So let me give the plausibility argument. First, go back to our old case where they were all equally probable. So if P is equal to 1 over W for, okay, sorry, it should be, all right. So let's say you had W options and P was equal to 1 over W for all options. Number of options was also W. Then log W is of course nothing but the log of 1 over P, which is nothing but the log. By the way, all logs are to the base 2. So I will not write that 2, which is minus log of P. P is a number less than 1, so its logarithm is negative, and you put the minus sign, becomes positive. Okay? So in the equiprobable case, minus log of P is fine. Okay? So in the general case, it's plausible, and of course, a great man like Shannon doesn't rely only on plausibility, but I will for the moment, equal to average value of log of P. Yeah.
There you mentioned the term ignorance. You said that.
Yeah, yeah.
What does that mean? I'm not a mathematician.
Uncertainty, are you happier with uncertainty? No, I certainly, I mean, the aim of these lectures is to convey information. So, that's why I picked this example, no? I don't know whether a coin is going to turn up heads or tails. So I'm ignorant. But once it lands, I know. So two options have collapsed to one. So the two, which was my initial ignorance, is the measure of how much I have gained after I have got the message. So it's two sides of the same coin. Ignorance before you receive the message is the same as enlightenment after you receive the message. I mean, that is the, since you mentioned this, one of the very bold steps which Shannon carried out, and he was aware of it, he wrote it down, is that his notion of information is independent of meaning. Right? In fact, he says, this is my definition of a message. It's a string of symbols governed by some probability distribution generated by some source. Messages may sometimes have meaning, I'm quoting. We'll come back to that. So, what would be the average of log p? Right? The average of log p, if you remember how one takes averages, is average of minus log p. So, you take minus log p1 and multiply it by p1 minus log p2 multiplied by p2 and add them all up. I remember this shocking experience in my 10th standard where the teacher suddenly wrote this Greek letter sigma. But I've got used to it. I hope some of you are. So I equal to 1 to s of pi log pi. So let's see how this works in practice. So we are really talking about very idealized messages at this point, but we will get to more realistic situations. So if you have an alphabet which consists still of two letters, say A and B, but let's say they now occur not with equal probabilities. Okay. So A, let's say, has some probability. Just to be concrete, let's say the probability of A is 1/4 and the probability of B is 3/4. Then you can actually work out how much this is, and you will get minus 1/4 log 1/4 minus 3/4 log 3/4. You add them up, you will get about 0.81. Incidentally, if you had chosen half and half, you would have got 1, because that's the case we have already discussed. If two events are equally probable, the information gained is 1 bit. Okay. And now you notice the information gained is actually less, it's 0.81 bits. Okay. So let me draw the graph of this function. So instead of 1/4, let's just see we had p and 1 minus p. Okay. So this is p, which goes all the way from 0 to 1, and on the vertical axis is minus log of p minus 1 minus p log of 1 minus p. Right? The generalization of what we just did here. Yeah, sorry, minus p log p. Right. So this is 1. So this is what the graph looks like. When p is half, you have 1 bit of information. If p is 1/4, you have 0.8 bits of information. Okay. Now, at the moment it's just a definition, all right. But one of the nice features of the theory which Shannon created was this definition proved to be useful. Okay. So if this definition is any good, it should imply the following. So suppose I have a message of 100 symbols, 1 all the way up to 100, and they are filled with A's and B's. But there are more B's than A's because of this particular assumption that we made, that the probability of A is 1/3 of the probability of B. So this measures 100 symbols. Now, each symbol is 1 bit in the sense, can be either a 0 or 1, though not with equal probability. Now, Shannon tells you that each is actually worth only 0.81 bits, which means this message of 100 symbols actually has around 80, or strictly speaking 81 bits of information. If that's really true, then I could code the message. I could convey the same information, but using some other 2 symbols C and D, or 0 and 1 with equal probabilities. Then they would carry 1 bit of information, and then I should be able to compress this to just a string of 80 characters. Okay. So this is called the Shannon coding theorem. Okay. I mean, if this definition is true, it should really work. Now, just to again make it plausible, imagine, let's take an extreme case where it was, 1 by 100 is the probability of A, and the probability of B is 99 by 100. Then it's pretty obvious how to compress the message. Basically, your message is going to consist of a long string of 100 B's with an occasional A, right? So you simply send the information about where the A's occur. A's occur in some 10 positions, and that will take definitely less than 100 bits of information. In fact, it will take even less than 80 bits of information. So in an extreme case, it's easy to see why, if P is not half, the message can be compressed. I hope this point is clear. And by the way, it's used all the time. I mean, if you watch movies, for example, you can make a simple count of how many pixels there are in each frame, how many frames there are per second, and if each pixel was independent and had the same probability, you wouldn't be able to download a movie in megabytes. It would take gigabytes, right? We'll come to that later. But I hope the fact that the moment the symbols do not occur with equal probability, the message can be compressed. At least as a qualitative fact is clear. But the beauty of Shannon is he makes it quantitative. He says that you work out the number of bits by this formula. I don't need a bar here. Okay, this is not a bar. This is the total. So this is H. It actually says that if a source is generating symbols with a certain probability distribution, which is not the flat probability distribution, then you can work out the actual number of bits per symbol, and then you can compress. He also gives some practical examples. If you take the English language, for example, in principle, in an English text, in any position, many things can occur. A capital letter, a small letter, a comma, space. So the number of possible symbols, which we called S, I think, is pretty large. So you could take the logarithm of that to the base 2, right? But of course, if you randomly threw these symbols into a text, it wouldn't be an English text. It wouldn't make any sense. Okay? So in reality, English text is compressible. Okay? Obvious example is SMS English, right? You have a thought in normal English, you create it in SMS English, and the person at the other end can, if they so want, convert it back to normal English. So in fact, and this is actually a more interesting case where number one, the probabilities of the different symbols occurring in one slot are not equal. E is the most probable, etc., etc. And it's also true that symbols in adjacent slots are not independent. Q is very usually followed by U, right? Now, it's actually a rather hard task to convert English text into a probability distribution and work out its entropy. So actually, Shannon, just since he was only illustrating a point, he drew a tentative conclusion that English is about 75% redundant. Okay? In other words, you could compress it by a factor of about 3. And I'm actually aware of, I think someone was sending around something which was an English passage where they did the following. They preserved the length of each word, the first letter and the last letter, and permuted the letters in between. But it was perfectly possible to read it. Right? Okay? So this whole notion of compression, which is such a vital fact of our lives today, the theorem underlying it is the Shannon coding theorem. So what the coding theorem says is, take a message, but really not take a message, take an ensemble of messages, a collection of messages described by some probability distribution, work out its entropy by using either this formula or a more general version of this formula. See, this formula refers to one symbol and it assumes that all the symbols are independent. Need not be. If there are correlations between the symbols, the formula works, except use some P which takes into account the correlations between the symbols. Okay. Work out H, and then Shannon tells you that you can compress it to H independent bits. Now, the nice thing about Shannon is he was being rather mathematical here. He actually proved that there exists a code which can compress an ensemble of messages which has H bits to H independent bits, okay? Even though the actual message might look longer. He didn't actually provide, so it's what mathematicians call an existential proof. It's there out there somewhere. It's a good thing that it's existential, because if he had actually given the algorithm, then a huge number of computer scientists, electrical engineers would have been unemployed. But as it happens, people are always improving compression algorithms and coding algorithms and so on. And what he did was therefore to provide the theoretical limit. If there is the source of messages which has a certain probability distribution, work out the entropy, and that tells you how much you can compress it. But interestingly, although this is very useful and very much part of today's technology, the real shocker in Shannon's work, which was the next step, okay, which he took. And it's more directly related to telecommunication. Okay. See, yeah.
I have one question.
Yeah.
So just going to DNA, for example, you have 4 bits, 4 letters that can.
Yeah. So let's say 2 bits.
2 bits.
Mm.
So how much can you compress it? And
That depends. Okay. First of all, do they occur with equal probabilities?
I don't know.
So then you put those 4 probabilities and work out this. But actually, this function is rather flat on top. So you might well find it's close to 4 unless one of them is close to 0. But more important, are there correlations between them? So you have to work out the entropy that way. He gives you the recipe. Yeah.
And this Watson pair kind of constraint.
Yeah, exactly.
No. In fact, that's such a perfect constraint that I would simply work out the entropy of one strand. And once you have one strand, the other strand is completely predictable. So therefore, that doesn't introduce any extra entropy. I mean, that's the way I would look at it. Okay. Remember, he worked in a telephone company. Today, your telephone conversations are actually encoded. Right? When you do voice over IP, what travels over that optical fiber is not your voice. It's a whole lot of bits. They're coded. I mean, some of them even travel by different routes and finally reach you. Okay, that's a miracle. But in his time, electrical version of the pressure variations in your voice was actually produced and went down a telephone wire. Okay? And as all of you know who have used the old-fashioned telephone, and perhaps still more the mobile telephone, especially in the current era, what is received is not what is transmitted because of what is called noise. Okay? All right? So then his next step was to look at communication in the presence of noise. Right? And then he proved a result which surprised people, okay, saying that given, again, his fundamental framework is always a source of information governed by some probability distribution, and then he also has to characterize the noise, which is, let us say, added to whatever you transmit. So that also has its own probability distribution. So for each of these, you can give an entropy. Okay? And then what he proved is that for a given source and for a given noise, okay, there is a notion called channel capacity. Okay? How much information you can transmit down this channel without any errors. Okay? Now that's what is surprising. Okay? In other words, in spite of the noise present, you want to transmit without errors. Again, to give you a very homely example, if you're on a bad telephone line and you're spelling out your name or something like that, you don't just say B, you say B for Bombay. Okay? So you're using up more resources, you're using redundancy in order to make sure that the message gets across. Or maybe you shout, right? Which may increase the signal compared to the noise. So the intuitive idea that there is a capacity for every channel, which depends on the level of noise and the level of your signal, had been floating around for some time. So his genius was in making it absolutely quantitative. Okay? And again, I'll give you a baby example. So the baby example is that let us say this telephone line, whatever information you are going to transmit is going to be as a voltage. Okay? And there are going to be 10 possible values of voltage, maybe standing for some 10 letters, or you're sending numbers maybe in decimal. Okay? So this is 1 volt, 2 volts, 10 volts. So this is at the transmission end. All right. Now, because of noise, it's a random phenomenon. 10 might become a whole distribution by the time it reaches you. Now, I'm going to choose a very artificial distribution for a favorable distribution, where the 10 can go anywhere between, okay, here is 9, and 9 can spread out like this. Right? It's 9 volts. We'll make sure that these distributions don't overlap. Now, the other thing I'm going to do purely for convenience is that assuming that voltage is a discrete variable. It's actually a continuous variable, but then we would have to deal with continuous probability distributions, which we may, as I said, that's the kind of thing I'm keeping for the end for the people who want, but we're not going to lose anything by that. So I think the example I have in my notes, this goes to 10.495 and this comes to 9.505, and then this goes to 9.495. So basically what one has ensured in this artificial example is that although this 10 is spread out by noise and this 9 is spread out by noise, the two don't overlap. Okay? So now at the receiving end, how do you decode? How do you decide what came in? So if you get anything, any one of these values, 100 values I think there are, you say that the input signal must have been 10. So this presumes that you have a knowledge of the noise properties of the channel. Likewise, so I mean this is a case where it's obviously going to work. You would be able to transmit without error, but let's ask what is the price you paid for that? If you look at the number of levels, so each one of these is multiplied into 100 levels. Okay? So at this place, you have some 1000 levels. I'm using the word level to mean voltage level. Okay? And here you have only 10 levels. Now, how did the 10 levels become 1000 levels? Because the noise took each one of these and multiplied it by 100, produced 100 different outputs for one input. Okay? So you can see that in order for this scheme to work, this has to be exactly the product of these two. Or in other words, entropy of the received signal will be equal to entropy of the transmitted signal plus entropy of the noise. I mean, it's a product when you talk of the total number of levels. When you take the logarithm to get the entropy, this is what you get. Okay? Now, this is the critical condition in which you are able to transmit the information without error. All right? In fact, this is what would be called an error correcting code. Error correcting coding of the signal. Notice that if you are greedy and you try to send more voltages with the same amount of noise, you would start getting errors. On the other hand, suppose you kept the noise level the same but increased the signal level, then in a way you are wasting resources, right? Imagine that you doubled everything. So this was 20, this was 18. Then you would have all this empty space here which you are not using. Okay? So in that case you are not using the channel to its full capacity. So the Shannon formula for channel capacity, so let me write down. Simply equals the entropy of signal plus noise, which is just a way of saying the entropy at the receiving end. And if you subtract from it the entropy of the noise, this is the maximum H entropy you can have at the input level and still transmit without error. Okay? Now I have to confess that this is a completely artificial example. Suppose we went to a more natural example. Each one of these has a Gaussian distribution. Now you can see you are in deep trouble, right? No matter what spacing you choose, it looks like you are still going to get errors. So this is where the genius of Shannon comes in. He says for any reasonable distribution of the noise, not necessarily this artificial rectangular distribution, but you have to be cleverer. You cannot encode a single symbol. Encoding a single symbol without error will simply fail. Okay? So the result that he actually proves is that, and again it's an existential result, where you prove that a scheme exists and then it's up to the engineers and scientists of the future to come up with that scheme. But he proves that the same formula, so now this entropy of the noise is not the entropy of a rectangular distribution, the entropy of some Gaussian distribution. Likewise, what you receive. Okay? It's still true that a scheme exists, and now this scheme has to be cleverer. It's not that you code each individual character. Maybe you code whole clumps of characters. And we'll see that there is actually a connection with StatMech here, which we'll come back to tomorrow. That it's very hard to say something about an individual molecule, but you can make more and more accurate statements about larger and larger numbers of molecules. And actually Shannon was not particularly trained in StatMech, so he seems to have discovered all this for himself. Okay? So I can give you a little bit of history. He introduced this P log P, and apparently he went around asking people, what should I call it? Okay? I've already given away the answer, entropy, but the way he arrived at that was that he talked to this great mathematician, von Neumann. So von Neumann, of course, has the reputation of instantly understanding whatever everyone tells him. And then he said, look, you should call it entropy for two reasons. One is a very similar formula was written down by Boltzmann long ago, and we will see that. The second is no one really understands what entropy is, and therefore by choosing this name, you will ensure that you will always be on the top of any argument. Anyways, all right. So I want you to appreciate that because I gave you such a dumb instance of this formula, that the actual formula is not so dumb. It works for any reasonable Gaussian kind of distribution of noise. Okay.
But Rajaram, I need to know the noise distribution.
Yeah, that you do need to know. I mean, if you were actually in a telephone company, you would test the line and you would work out the noise distribution. And let's say, see, telephone, okay, because of the redundancy of speech, even if some things go wrong, you can afford it. But imagine you're sending data. You don't want the data, I mean, what occurs all the time in this room. So then, I mean, how many times have you encountered, you download movies, huge files, they just come through without error, right? And that's precisely because, of course, people could be very conservative. They could work at well below the channel capacity. By the way, I told you Shannon's proof was existential. I should also tell you it was asymptotic, because it's very obvious that if you had only one symbol, a very short message, it's never going to work. The distributions overlap, and it is absolutely true that a given received signal will correspond to more than one transmitted signal. So his result that you can have, it's one of those epsilon delta things. He says, okay, you want error probability less than some very small number. I can tell you that if your length of message is more than such and such, I will give you a coding scheme in which you can reduce the error probability to less than that. So I can assure you that all the protocols which are used for exchanging information on the internet and so on use error correcting codes. But of course, the telephone companies and the internet companies have to make money, so they will push you as close to the channel capacity as possible. Okay. Now, how am I doing for time? Okay. So then this is going to be a bit of a digression because I doubt that it has application in biology. Okay. But it's very close to communication. So now let's look at what is actually the capacity of a telecommunication channel, which is really the problem that he wanted to tackle. Okay. Now you already have a kind of idea of it from here, that the channel capacity is going to be something like the log of signal plus noise divided by noise, bits. But this is still bits per sample. I've still been talking of only one character of the message. So there is a missing link here. When you're talking over a telephone channel, how many characters or how many voltages are actually being sent to you per second? Okay. Now at first sight that might appear to be infinite. Okay. This is some voltage representing speech, and it looks like there's an infinite number of voltages which are being transmitted because the time axis is infinite. We have already overcome one infinity. Okay. It's also true that each voltage can take infinite values. Even if you limit it to 10 volts or something like that, the number of real numbers between minus 10 volts and plus 10 volts is infinite, I mean uncountably infinite. Okay. What our discussion so far has shown is that's not really infinite, because it really should be measured in units of the noise. I mean this is a almost trivial remark, but if we don't take account of noise, the entire Encyclopedia Britannica could be transmitted in one real number, because right now it is stored as zeros and ones on some computer. So just put all those zeros and ones together, one after the other, and you will get a long string of zeros and ones, which is a real number, right? Now, what makes this scheme impractical is that you could never transmit this real number with fantastic accuracy to anyone else because of presence of noise. Okay. So even though this looks like a continuous voltage as a function of continuous time, this axis from the information point of view is not really continuous, right? There's only a finite amount of information in each voltage because of the presence of noise. The other bit, which actually was known before channel, is that although time is continuous, this signal can be reconstructed from a set of samples which are finite in number. Okay. All right. Now that might seem a little odd, and the reason actually is, so this is something called, there's one more name I'd like to introduce. It's called Nyquist sampling theorem. Nyquist is actually again Bell Telephone Labs. It's sort of amazing how an industrial lab produced so many interesting fundamental concepts. Okay. What this says is that any actual signal you send over a telephone line doesn't contain all possible frequencies. It can't, right? It contains a finite range of frequencies, which is exactly what we call bandwidth, B. It's either measured in hertz or cycles per second. So that means if you want to build up this curve by superposing sine waves and cos waves, you don't have access to an infinite number of them. You have access to as many up to this bandwidth. Or in more familiar terms, the signal cannot vary infinitely fast. If I know the value here is not independent of the value here. So I cannot count them as independent samples. So then the question is, how many samples are required to reconstruct this signal if I am given the information that it has a finite bandwidth? So again, I'm going to write down a number which is intuitively clear. It's twice B into T samples. Okay. T is the total time. Obviously, given enough time, you can send plenty of samples. I think a better way to write this is T divided by 1 over 2B. So B has the units of hertz or inverse time. 1 over 2B has the units of time. So what this means in practical terms is, let us say this is the sine wave with the highest possible frequency in your sample. So then if you sample here and here, that is twice per cycle of the sine wave, then you will be able to reconstruct this sine wave and all other sine waves as well. Okay? So this is the Nyquist theorem. Again, I know that if there are theoretically minded people in this audience, they won't be satisfied with this, but we always have session 4 to sort out that. Okay? So now you basically understand what's happening in the mobile revolution around you, why people are fighting and scamming and so on for bandwidth, because you can send more messages, provided you respect the channel capacity and you do the proper coding and all that. It's also true that it helps to have a stronger signal, right? So that's why you fight for more mobile towers, so that you get a stronger signal and so on. Right? So I just thought, so there is a famous formula which incorporates both these features, the logarithm of this. So that formula is, which I won't derive, is just b times the logarithm to the base 2 of 1 plus s over n. And now this is a rigorous formula. So, sorry, yeah. So s is,
Maybe you don't write.
oh, okay, I don't write there, right. Yeah, and okay, this formula was for this very particular case, and it was for one sample. So the general formula is b times the log to the base 2 of 1 plus s over n. So if your mobile tower generates a certain level of signal, and then the level of noise is certain. By the way, noise will arise even in the transmitting electronics, need not be in the cable and so on. Then this sort of rigorously defines the channel capacity. Now notice that it's much better to pay for B rather than to pay for S, because increasing signal strength is just sitting inside the logarithm. So once S over n becomes significantly more than 1, this logarithm is a curve which rises very slowly. Okay? So, I mean, some of you may know that I spent some 13 years in the National Center for Radio Astrophysics in Pune. The same Bell Telephone Labs which invented lots of this stuff also invented radio astronomy, but these two are in direct conflict with each other. Okay? So one of the reasons why I learned some of this communication theory was so that I would be more informed in discussions with telecom companies who wanted to put mobile towers near our telescopes, okay, in order to persuade them to go to a certain distance, and so in a sense I learned this bit of information theory in the spirit of know thy enemy. Okay, so this is a kind of introduction to the original context in which information theory arose, and what we need to take away from it right now is that there is a nice logical measure of the uncertainty or ignorance associated with a probability distribution, and it can be just converted to bits and called entropy, and this definition is actually useful. It enables you to compress things. It enables you to do error correcting coding. And I'm sure I told you about the reliability of the internet transmission that you receive, but there's a more fantastic example of reliability in this room. I mean, we are all here in spite of all these noisy processes going on inside our bodies. I'm sure you will learn much more about that in the actual workshop, but surely there must be some kind of error correcting coding going on in your bodies. Okay, so I'll stop here, and let's have, what would you say is a decent break?
Yeah, 15 minutes.
Yeah.